Bismillahirrahmanirrahim. In this part B of lecture 8, we'll talk about distance vector routing algorithm, and we'll also cover border gateway protocol. In the previous lecture, we have talked about link state routing algorithm, right? And we have covered the algorithm and its working in detail. And we also discussed the routing protocol that is making use of link state routing algorithm, means open shortest path first routing protocol. So this distance vector routing algorithm is basically based on dynamic programming, right? So let's talk about some of the basics of this distance vector routing algorithm before discussing the algorithm in detail. So we're interested in discussing distance vector algorithm. So this distance vector routing algorithm is based on its origin is basically the class of algorithms known as dynamic programming. So I hope you might have covered the dynamic programming in your design analysis algorithms class, but here, this word dynamic means, this means multi-stage. Or time-varying process. Time-varying process. And programming, obviously you're familiar with the programming means planning, or we can say decision making. Decision making by a tabular method, specifically if we talk about this distance vector algorithm by a tabular method. Right. So this distance vector routing algorithm is based on basically dynamic programming, and the word dynamic means there is multi-stage or time-varying process, and programming we are familiar with means we're planning, we are solving, we are making a decision by solving something there by using a tabular method. So we use this dynamic programming when a problem can be divided into subproblems that overlap. So dynamic programming is used when a problem can be divided into overlapping subproblems that overlap. Okay, and we can solve each of these subproblems once, and then store its solution, say in a table, right? And if, for example, the subproblem is encountered again, we can simply look up its solution in the table. So we can like reconstruct the solution to the original problem from the solutions to the subproblem, right? So this means the more overlap is the better, as it reduces the number of subproblems, right? So so basically what it does is, so it solves each subproblem. Once and store the solution. Say in a table. And whenever we, encounter the same problem, so we do not need to compute it again and again. So what we can do is we can reconstruct. So this means we can reconstruct the solution solution to the original problem. From the solution to the subproblem, right? From the solution to the subproblem. All right, so that's why if more overlapping is there, so this will reduce the number of subproblems. Usually, this dynamic programming is used to solve optimization problems, right? So we use dynamic programming to solve optimization problem. For example, you're asked to find the shortest. Please find the shortest, or maybe best, the best way of solving a problem or doing something. Okay, so in other words, there must not be an optimal solution that contains suboptimal solution to a subproblem. This is very important to note. So this means there must not be an optimal solution that contains suboptimal solution to a subproblem, obviously, to a subproblem. Okay, so the solution of the subproblem has to be optimal also in order to have the optimal solution of the problem, right? So this distance vector was initially proposed by Bellman, right? So Bellman in 1957 proposed Bellman's shortest path algorithm, right? Bellman's shortest path algorithm. And initially, it was centralized. It was not distributed, because we know distance vector routing algorithm is distributed in nature, right? So initially, it was centralized distance vector algorithm. So initially, it was centralized distance vector algorithm. Then later on, Fulkerson in 1962 modified the centralized algorithm proposed by Bellman to propose a distributed version, right? So Fulkerson in 1962 modified the originally proposed algorithm by Bellman, modified Bellman's algorithm. To a distributed version, right? And by the way, this distributed version is also known as Bellman-Ford algorithm, right? That we'll cover in a minute, right? So coming back to the Bellman-Ford algorithm, so now we know that the Bellman-Ford algorithm is based on dynamic programming, where we divide a problem into sub-problems, and then we try to find an optimal solution of a problem. Means the shortest, in this example, for example, we'll try to find the shortest path, right? The best path to reach from source to destination. So again, here we have some of the notations that we need to understand before discussing Bellman-Ford's algorithm in detail. So this notation dxy, d sub xy, is the cost. In fact, it's the least cost path from a source x to destination y. So here this x is source, and this y is destination, right? So and how we can compute the least cost path from x to y? Yes, the least cost path from x to y is in fact a minimum of the cost to reach from x to its neighbor b, right, plus the least cost to reach from its neighbor v to destination y. So this means we have to identify a minimum path that is taken over all the neighbors of v. So what we will do basically is we will calculate this value for all the neighbors of x, and we will select a path where reaching from x to y is minimum from a specific neighbor. Okay. So so if we look at this problem of finding the least cost using Bellman-Ford equation, so what do you think was the cost to reach from it's the same example, by the way, that we used in the last lecture. So what do you think was the least cost to reach from u to z, right? So what you will do, you will find the cost to reach x from each of its neighbors. So it will find the cost to reach z via v, right? To reach z via w, to reach the destination z via x, and it will select a path which is the shortest path to reach the destination over all the neighbors. And similarly, this will be happening distributedly on its neighbor as well. So x will again find a cost through its neighbor, which is minimum to reach the destination z. Similarly, we will also try to find a cost that is minimum through some of its neighbor, through one of its neighbor to reach the destination z, right? So what here we are doing is, so we are calculating the cost to reach from router u to its neighbor v, the cost to reach router u to its neighbor x, the cost to reach from U to its neighbor W. And it's, by the way, it's known why, because these are the direct neighbors of U. Now, we will find a least cost, and same is the case with the neighbor X. So this cost is known, we know this cost 2, so we can see here, right? And similarly, this cost is 1, the cost to reach from U to X, and the cost to reach from U to W is 5, right? But what's the least cost to reach from V to Z? So what's the least cost to reach from the neighbor V to Z? Yeah. So the least cost from V to Z is from V to X, which is 2, and then from X to Z, which is 1 plus 2, 3. So 2 plus 3 is 5, right? So again, X also calculates its least cost to reach Z, which is 3, and W also calculates least cost to reach Z, which is again this path, right? From Y to Z, it's 3. So we'll select the shortest path, which is via neighbor X, right? So the shortest path is via neighbor X, right? So in this way, we'll try to identify, using Bellman, for the shortest path that is taken to reach a specific destination over all the neighbors of the source router, which is U in this case. Right. So so this distance vector routing algorithm is distributed, means every node communicates only with the directly attached neighbors. It's iterative. There is no stop signal here. So it continues until there is no node to exchange information, right? And it's basically, we always stay in a loop and wait for a link cost change that we'll see in a minute. So it's self-terminating, and the machines or the routers does not need to, the router or the nodes need not to exchange any information. So let's try to expand this notation, since we have seen that in order to reach from this source X, this is the source, remember, to destination Y, the important factor is the neighbor, right? So I have modified, so we have modified this representation or this notation, where now it is written as the cost to reach from X to Y via Z, right? So this is the distance from X to Y, where X is the source, D is the destination, via Z, as next to means Z is the neighbor in this case, right? So this Z is neighbor. Okay. So now if I want to calculate this cost, so what I have to do is, yes, first of all, I have to calculate the cost from the source to the neighbor Z. So this is what is happening here. So we have to calculate the cost to reach from the source to the neighbor Z, and then we have to again calculate the minimum cost to reach from the neighbor Z to destination Y via some of its neighbor, say W. So again, Z has to explore all of its neighbors to see which one contain the least cost to reach the destination, and then we'll add these two costs together to find the distance to reach from X to Y via Z. So let's try to look at the algorithm first. So it also has two steps. This algorithm, distance vector routing algorithm, which is Bellman-Ford algorithm at the moment that we're discussing, it has two steps. It has an initialization step, right, where for all the adjacent nodes V of a source, if the node, the destination is not the direct neighbor of X, the cost to reach the destination is infinity, right? So this means that the destination is not the direct neighbor. And if the destination is the direct neighbor, the cost to reach from X to V is known. Why? Because V is the direct neighbor of X, right? And for all the destinations Y, what we'll do is we'll send the minimum cost to reach from X to Y, obviously some of its neighbor W. So what happens in this initialization step is, again, we'll have the same we'll follow the same steps as we did in the last class. So first we'll look at the algorithm, we'll try to solve an example, and then we'll again come back and try to understand the algorithm. So in this initialization step, to simply if a node is directly attached with the neighbor, the cost is known, and if a destination is not directly attached with the neighbor, the destination is infinity. And then when a cost is known to reach a specific neighbor, so we need to exchange this cost with the other neighbors. So X will exchange this cost to reach destination Y with each of its neighbors. So after this initialization step, we enter into a never-ending loop, right? So what happens here is that a node waits for what? Until there is a link cost change to a neighbor V, or there is an update from neighbor V, right? So if a link cost between, say, router X and V has changed from 2 to 3, right? Or V informs the router U that a cost to reach a specific destination has changed. So if the cost to reach from X to V changes by D, I mean, this change can be, positive as well as negative. So we have to recalculate the cost to reach all the destinations, right? So else, if the update is received from V with respect to some destination Y, again, what we have to do is we have to again calculate the new cost, right? And if the new cost is minimum, we will send this update message to all of the neighbors of V, and we'll again we'll stay in this loop, and we'll wait for two things to happen. Either a link cost has changed, that is the cost from X to V. So if it has changed, the cost has changed, we will recalculate the cost, right? Or else we'll wait for an update from V with respect to some destination Y. Again, we'll calculate the new cost, right? And if the new cost is minimum, we will communicate this update with our neighbors. So let's try to see how it works with the help of an example, and then we'll again come back and try to understand this algorithm. So what happens basically? So a node has to wait for a change in the link, number one, or a cost message from the neighbor. And then what we have to do is we have to recompute the distance table. And if by recomputing the distance table, we come up with the new least cost that we have to notify to all of our neighbors. So each iteration in the loop is caused by either a local link cost change, means the cost from U to V has changed, or there is a message from its neighbor that there is a new least cost to reach some of the destination, right? So each node notify neighbors only when, this is important to understand, when its least cost path to a destination has changed, right? And then the neighbors notify their neighbors, and then so on and so forth in a distributed fashion, right? So let's see, and let's try to understand the working of distance vector routing algorithm with the help of this example. Okay, so here we have 3 routers, and this is the link cost associated with between each pair of routers. The link cost between X to Y is 2. The link cost between Y to Z is 1. The link cost between X to Z is 7. So every node has its own distance vector table, right? And let's try to understand the distance vector table here, that what it represents. So this table of X has rows and columns, where the rows represents the destination. So the rows represents the destination, whereas the column represents the neighbor or wire, right? So the column represents what? So the column represents neighbor, okay. So look at the table of X. So what are the different neighbors of X? Yes, Y and Z. So what are the entries here? Y and Z, because Y and Z are the neighbors of X. And what are the destinations, by the way? Yes, Y and Z, right? Because these two are also the destinations, possible destinations for X. So this here represent in columns neighbor via. The rows here represents the destinations, right? So this this table might have looked different if I add another node here, another router here. Let me just assume that here is router T and its cost is 2. So what do you think, where will be the change in this table? In rows or columns? Yes, there will be no change in columns. Why? Because router T is not the direct neighbor of X, but yes, router T is another destination, right? So in columns, we'll have all the neighbors, and in rows, we will have all the destinations. Okay, so as per the algorithm, in the initialization step, if a destination is an adjacent node of the source, the cost is known, which is true here. Why? In the case of destination Y. Why? Because Y is the direct neighbor of X, and this cost is known, being the adjacent node. So this cost is 2. Why? Because it's the direct neighbor. And look at this cost, and also learn how we're gonna read it, right? The cost to reach from X to Z via Z, right? So this is the cost, the distance to reach from X to Z via Z. So what does this mean? That Z is the direct neighbor of X, right? The cost to reach from X to Z via Z. The cost to reach from X to Z via Z means Z is the direct neighbor of X is 7, right? So so we have learned how these two costs are being represented in the table. But what about this cost? How are we gonna read this cost? So this cost is the cost or the distance to reach from X to destination Y via neighbor Z, right? But this cost has not been in this initialization step. This cost has not been communicated to X by Z. So this cost is infinity to start with, right? So we have no information. Why? Because Z has not exchanged this information, that what's the cost to reach from Z to Y with X. So at the moment, this is infinity. And what do you think? So this cost is infinity, and it is being represented here. And what do you think was the cost to reach from X to Z via Y? And again, we can write it. I will write it one more time. That is the cost to reach from X to destination Z via Y. So X to Z via Y. So what is this cost? This means this is the cost from X to Z via Y, and Y has not, since we are in the initialization step, Y has not communicated this cost with X. So that's why again it is infinity. So this is the situation in table distance vector table of X in the initialization step. Similarly, we have the table for Y, and what it says, which are the neighbors of Y? X and Z. So in columns, we have X and Z, and X and Z are also two destinations, right? And if I assume that there's another router T, so what do you think where we have to change for Y? Yes, we have to add T here as well in the column Y, because T is the neighbor of Y and T is also a destination, so we'll also add T here. Okay, so what do you think was the cost to reach from Y to X via X? Means X being the direct neighbors. What I'm saying is, what is the cost to reach from Y to X via X, right? So it means This is the distance to reach from y to x via x, means x being the direct neighbor. So the cost to reach from y to x via x is 2, right? We know this y because it's an adjacent node, so it's known. Similarly, what's the cost to reach from y to z via z? Y to z via z being direct neighbor, this cost is 1, right? And what do you think? What's the cost to reach from y to x via z? So what I'm saying is y to x, but via z. So z has not communicated any information at the moment. So this cost is not known. So it's infinity. It's the cost to reach from y to z via x. Y to z via x, right? So again, x has not communicated this cost with y. So it's again infinity, right? So, and obviously, you can notice here that what do you think was the least cost to reach from y to x? Yes, infinity or 2? 2. So what I've done is I have marked this cost as least cost using this circle. And similarly, we have the table of z. So what is the least cost to reach from z to x via x? Z to x via x means x being the direct neighbor of z to x via x is 7. So adjacent node known, so right. Then what's the cost to reach from z to y via y? Z to y via y, again the direct neighbor, the cost is known, 1. And what do you think was the cost to reach from z to x via y? Z to x via y. So y has not communicated any information with z, so this cost is not known, infinity. And similarly, the cost to reach from z to y via x, again x has not communicated this cost with z, it's infinity. So in the last step of initialization phase, what we do basically is once we have known the cost to reach the other destination, for example, in the case of this y and z. So what y will do? Y will send update messages to its neighbor. So y will send update messages to z and x. Similarly, z will send update messages to x and, yes, you're right, y. And similarly, x will send update messages to y and z, right? And what x has to tell, for example, what y and z has to tell, these least cost to reach to certain destinations, right? So let me go back and look at the initialization step of the algorithm. So, in the initialization step for all adjacent nodes, if v is the direct neighbor of x, so this means the cost is known, that is the cost to reach from a node x to destination v, where v is the direct neighbor. And if it is not known, the cost is infinity, okay? And once we have this initial cost, so what we do basically, we share this minimum cost with each other to update our tables, right? So what will happen if we look at this? What will be the message that x will be getting, right? So see, what we are doing here is that in the initialization step, we are getting this cost for this update messages from y and z. So x will receive update messages from y and z. So what is the update message from y? What do you think? So what y has to tell to x? So y has two costs here. The cost one is to reach from y to x. Probably x won't be interested in this cost, right? So what about the second cost here? The cost to reach from y to z. The cost to reach from y to z is 1. So this is a message from the neighbor y, and we will update this table of x using this message. So this is this message here, right? So how, and using this equation, we will update the table of x. So what it says is the cost to reach from x to z via y. So this via y here is telling me that the update message is coming from the y, right? To reach destination z. So what is the cost to reach from y to z is 1, right? So we'll do first, we'll calculate the cost to reach from itself to y. So if we look at the table, what do you think was the cost to reach from x to y? Yes, 2. That's because y is the direct neighbor of x, and we have this cost in the table as well. So it's 2. And what's the minimum cost from any of the neighbor of y to reach the destination z, right? So if we look at this update from here, this cost is 1. So the cost to reach from y to z via z, because z here is the direct neighbor. So if I modify this equation, this would be, and in fact, it would be this, right? So the cost to reach from y to z via z, right? So y to z via z, it's there in the table, is 1. So the cost to reach from x to y is 2, and the cost to reach from y to z is 1. So this cost is 3, right? So we are talking about this cost, which was initially what? Infinity. Okay, so this is the cost to reach from x to z via y, right? So neighbor y. What's the cost? 1. So what's the cost to reach from x to y? 2. So 1 plus 2, as we have seen in this equation, it's 3. So this is the new least cost, by the way. Previously, the least cost was 7. Now we have a new least cost via neighbor y. So if I want to send data from x to z, so the least cost is from x to y via x to z via y, right? So we have the new least cost, and I have marked here the new least cost. And similarly, z is also sending a message, update message to router x. And what z has to send, if you look at the table of z, yes, the first entry is the cost to reach from z to x via x. Obviously, x won't be interested because z is the direct neighbor of x. But look at this second information here. The cost to reach from z to y via y, right? So it sends this information to x. Look, if you want to reach from me to y, the cost is 1. And what x does is, it says, okay, fine, what's the cost to reach to my neighbor z? 7. So 7 plus 1 is 8. So the cost to reach from x to destination y via z. So I'm talking about this cost, the cost to reach from x to y via z, okay, which was previously what? Infinity. So what I have to do for in order to calculate it? So first I will calculate the cost to reach from x to the neighbor z, and then whatever is the update that is being shared by z, which is the cost to reach from z to y via y. So z to y via y, which is 1. Okay, so 7 plus 1 is 8. So we have a cost update here, but obviously this is not the least cost, right? So still 2 is the least cost, right? 2 is less than 8, so that's why it's the least cost. And similarly, in order to calculate the table of y will receive updates from x and z here, right? And z, for the calculation of z's table, z will receive updates from x and y, right? And we can again see the situation in the table of y and z. So look at the table of y. So this entry was already there, 2 and 1. So what has happened here? So this is the cost to reach from y to x via z. So this means I can understand that this message is this least cost change is because of the message update message from z. So what z has to tell y? So again, we look at the table of z here. So z has 2 costs: the cost to reach from z to y via y being the direct neighbor. So obviously y won't be interested in this cost. But look at this cost: the cost to reach from z to x, which is 7. So z informs y that the cost to reach from me to x is 7. So it says, okay, fine. So the cost to reach from my neighbor Z is 1, and the cost to reach from Z to X is 7. So the cost to reach from Y to X via Z is 8. So the cost to reach from Y to X via Z is 8. But this is not the least cost. Obviously, there is an improvement because previously this cost was infinity. We have updated a number, but this is not the least cost. Similarly, look at this cost, the cost to reach from Y to Z via X. This means this update message is coming from X. So what we have in the table of X, the cost to reach from X to Y, which is 2. Obviously, Y won't be interested in this cost. And what is the second cost? The cost to reach from X to Z via Z, which is 7. So what X is telling Y, that if you want to reach from me to Z, the cost is 7. So what Y calculates is that the cost to reach its neighbor X is 2 plus the cost that X is advertising 7. So this means if Y takes this path to reach the destination, the cost is 9. So the cost to reach from Y to Z via X, via means through neighbor X, the cost is 9. So using the same equation that we have discussed in the previous slide, we will calculate this cost. And obviously, this is again not the least cost, okay? Because 1 is the least cost. And what is happening here in the table of Z? So in the table of Z, here we have this update, that is the cost reached from Z to X via Y. So this means this message is coming from Y. So what's the situation in Y? So there are 2 entries here. The cost reached from Y to Z via Z means Z being the direct neighbor, and the cost reached from Y to, and Z won't be interested in this value obviously, and the cost reached from Y to X via X means 2. So what Y is telling Z, that if you want to reach from me to X, the cost is 2. And what's the cost from Z to Y? 1. So 1 plus the cost from Y to X to 3. So we have here this cost 3. That is the cost reached from Z to X via Y. And Y tells the cost reached from Y to X is 2. And the cost reached from Z to Y is 1. So 1 plus 2 is 3. Right? So here we have 3, and it's also the least cost, right? Because it's less than 7. And similarly, look at this value here. The cost reached from Z to Y via X. So this means this update message is coming from X. So what X has to tell to Z? The cost reached from X to Z via Z, 7. Obviously, Z won't be interested in this cost. And the next is telling Z that the cost reached from X to Y is 2. Right? So what's the cost to reach from Z to X? 7. So 7 plus 2 is 9. So here we have this cost 9. Okay. So then in the loop, we wait for the least cost to change to a destination. And yes, this is the case here. What do you think? Which router will send the update message now? Is there any change here in the table of Y? No. I mean, in terms of the least cost. The least cost is still 2 to reach destination X, and the least cost is still 1 to reach destination Z. But do we have a change here in X in terms of least cost? Yes, there is a change here. The least cost has changed from 7 to 3. So this means X will send update messages to Y and to its neighbor, to Y and Z. Okay. Is there any least cost change in the table of Z? Yes, there's a least cost change here. The least cost has changed from to reach from X to reach from Z to X has changed from 7 to 3. So this means Z will send update messages to its neighbor Y and X and Y, but there won't be any update messages from Y because the least cost has not changed. Right? So again, if I go back to the algorithm and see that in the loop, we wait for 2 things to happen. Number 1, to see a link cost change to a neighbor V, but this is not the case that we are discussing at the moment. But yes, there is an update from neighbor V to some destinations, right? So if there is a change, what we'll do, we'll calculate the updated cost in each table using this equation, and if so we're using this equation, and if there is the new cost is minimum, so we're gonna again re-notify to all the neighbors. Okay. So so what do you think? So this means X will receive update messages from, yes, Z only, right? Because Y will not send any update message. So what is the update message that Z has to communicate to X? So look at this change, right? Z has to inform X that the cost to reach from Z to X has changed from 7 to 3. So do you think, will there be any change in the table of X? That Z is telling X that its cost to reach X has changed? No change, right? So it will bring no change at X. Okay, so there will be no change here. And similarly, what message X has to inform to Z? What's the change here? So X has to inform Z that the cost to reach from X to Z has changed from 7 to 3. So what do you think? Will we have any improvement here in the table of Z? No. So no change in the table of Z. But there is an interesting change here in the table of Y that we have to understand, right? So let's look at the table of, so you can see there's no change in the table of X, it's the same, right? There's no change in the table of Z, it's also the same, no improvement here. And by the way, there is also no change in the table of Y in terms of the least cost. So least cost is still the same, right? I've just said, but this is important here. So we have some new values here that I want to discuss with you, and I want you to pay attention, understand it, right? So because this will help us to understand the problem, the shortcoming of distance vector algorithm. Okay, so what is this cost? So this means this is the cost to reach from Y to X via Z. Okay, so this means this is the cost, by the way, that I'm talking at the moment with you, is the cost to reach from Y to X via Z. So this means this update, this change is because of the message from Z. So what is the message from Z? What was here with Z to communicate? Yes, the link cost to reach from Z to X is 3. So Z is telling Y that the cost to reach from Z to Y has changed from 7 to 3. And Y says, okay, fine. What is the cost to reach from me to Z? 1. So 1 plus 3 is 4. So we can see a 4 here. But there is a problem with this path or with this cost. It involves loop. And loops are not allowed in networks. Remember, loop is not allowed in networks. And what do you mean by loops? Means a packet should not visit a router more than once, right? And if you focus on this path 4, what is this path, right? So this Z is telling Y that the cost to reach from Z to X has changed to 3, right? And the cost to reach from Y to Z is 1. So 1 plus 3 is 4. So what happens basically is, if I take this path, by the way, this path is not taken, but this can create a problem. We'll see in a minute how, right? But I just want to make you understand that how it creates a loop here. So this means if this path is selected by somehow, this means what? This means that Y will first send a packet to Z, right? And look at the Z's least cost to X. Let's go to the Z. And what is the least cost of Z to X? the cost reached from Z to X via, and this least cost is via Y. So this means Z will again send this message to Y, and via Y it will go to destination X. So this means there is a loop here. This packet is visiting Y more than once, creating a loop, right? So this path involves loop, and this will never be selected, by the way, but this can create problem in the convergence time of the algorithm, means the number of iterations that an algorithm has to do in order to be in a stable state. We'll see in a minute how. And similarly, look at this path also, this path. This is the path to reach from Y to Z via X, right? So this means the message is from Y. The change is because of the message from Y, and so from the change is because of the message from X. So what is the message from X? What X has to tell to Y? Yes, X is telling Y that this least cost has changed to 3. So X is telling Y that the cost to reach Z has changed to 3. So Y says, okay, fine, the cost to reach from me to X is 2, and X is advertising the cost to reach Z is 3. So this cost is 5, which is here, right? This again involves a loop. If this path is selected, right, this means what? Is Y will first send message to X, and then we go to X and we see the cost to reach from X to Z is 3, which is the shortest cost via Y. So this means again, if Y selects this path, Y will first send this message to X, and X will again send this message to Z via Y, and again there is a loop here at Y, right? So again we have a loop here. So this means this can create problem for us in terms of the convergence, the number of iterations required for the convergence of the algorithm. This problem needs to be taken care of. That we'll see in a minute how we can cater this problem. So allow me to go back to this algorithm here so that see if it's clear to us or not. So in this loop, our node will wait for two things: either a link cost has changed to a neighbor, or there is an update from a neighbor with respect to some destination B. So we have covered this part, right? So we have covered this this part, and if there is a link cost change by D, so we'll calculate the new cost, and else if we receive an update with respect to some destination Y that we have seen in the example, so we will again calculate the new cost as we discussed, and if the new cost is the least cost, so we have to communicate this least cost to with all our neighbors. And if this new cost is not the least cost, which was the case with Y, so there won't be any update messages for the neighbors, and we'll again remain in this loop waiting for either a link cost change or an update with respect to from a neighbor with respect to a destination, say V. Okay, so now I would like to discuss this problem of looping, and see what are its effects and how we can taken care of it, right? So again, look at another scenario, and here there are also loops in this table. For example, look at this path: the cost reached from E to A via D. So what I'm saying is I want to go from E to A, but via D, right? So the cost reached from E to A via D is what? So this means E will first send message to D, and D's shortest path is via E, right? So this means there is a loop here, right? So this cost means the cost reached from E to A via D here involves a loop. Similarly, look at this cost reached from E to A via B. Again, I want to go from E to A, but I want to go from E to A via B. So first I'll send message to B, and B's shortest path is again via E. So again, we have a loop at E, right? So this means obviously this loop path is not the shortest path or the least cost path here. But we need to see how we can address it. So by the way, before we move forward and discuss how these loops can create problems, so this distance table that we have just discussed gives us the routing table, right? So in routing table, for example, we have the destination and we have the outgoing link. So if I want to, and the cost associated with it. So if I want to go from E to B, the outgoing link is the link attached with router D. The next hop is router D, and the cost is 5, right? And similarly, if I want to go to destination, reach destination C from E, the next hop is D, and the cost is 4. So this distance table is used to create the routing table to make a forwarding decision based on the least cost path. Okay, so let's see how the least cost change can create a problem and can result in a loop. So let's assume a sunny day scenario. There's a good news that the cost has changed from y to x to from 4 to 1. So what happens here is that at time t naught, we notice that the cost from y to x, y to x via x means x being the direct neighbor has been changed from 4 to 1. So obviously this is the new least cost, and as soon as y learned about this new least cost, it informs its neighbors. So it will inform its neighbor z that it has a new least cost, right? And immediately the neighbor z will say, okay, fine, the cost reached from me to y is 1, so 1 plus 1 is 2. So it also has the new least cost that is 2, and then it informs y about it. And after a couple of iterations, the algorithm terminates or is in a stable state. Okay, but look at the other scenario. What if the least cost has changed from 4 to 60? Then what do you think? How many number of iterations are required? Do you think that the algorithm terminates in a couple of iterations? No, right? So it's a bad news, and bad news travels slowly, right? So, for example, if you have been unable to pass a course, so this news takes a lot of time to reach your parents. So it's a bad news. But if it's a good news, you have topped in a course or in a semester, so you will immediately call your parents and friends and family friends to tell them that you have secured a good grades. So this can create count to infinity problem, right? How? And this is because of the loops in the distance table, right? So let's see how. So look at this table of y before this change. The cost reached from y to x. The y to x, y-x means x being the direct neighbor is 4. And I want you to understand this cost, right? And this cost is the cost reached from y to x via z. The cost is from y to x via z. So this means if y has to send message to destination x, but via z. So what is this cost? 6. So this means y will first send this to z, and look at z's table. The cost to reach from z to x via y, which is the least cost, is 5. So this means z's least cost is via y. So this means the 6 means y will send a packet first to z, and z will again send it via y. So obviously, what is here? Yes, you're right. There is a loop here. Okay, a packet is visiting more than once to this node y, router y, and that's why we'll see this will create a problem here. This bad news. So at t naught, the y has noticed a change here. That the change is the cost has changed from 4 to 60, right? So immediately when this cost has changed from 4 to 60, it has selected the path which involves loop, right? So it immediately selects 6 as the shortest path. So it informs z that the new least cost is 6. So y is telling z that the new least cost is 6. So y says, okay, fine. The y is telling z that the new least cost is 6. So z is saying, okay, fine. The cost to reach from me to y is 1. So 1 plus 6 is 7. Again, z tells y that the cost to reach from me to x is 7. Right? The cost to reach from z to x y is 7. And y again says, okay, fine. What is the cost to reach from me to z1? So again, the cost to reach from y to x via z8. So because of this loop, 50 plus iterations in order to have the algorithm in stable state, and that's why we call it a count to infinity problem, right? So we have to do more iterations in order to select the right path, right? And the solution to this problem is Poisson reverse. We need to Poisson the reverse path, means the path involving the loop, right? So see, there is no reverse path here. So I have declared it infinity. Okay, and when we talk about RIP, because RIP makes use of this distance vector routing algorithm, RIP protocol. So what happens in RIP is this infinity is equal to 16. So if 16 is mentioned there because the maximum number of hops that are allowed in RIP are 15. So if I mention 16 here, this is equivalent to infinity, right? So what happens here? Now again, look at the same problem, that after T naught, there is a change in the link cost between y and x, and the cost has changed from 4 to 60. Okay, so immediately the new, and rightly so, the cost is selected, which is 60. And now it informs z that the cost has changed from 4 to 60, and it says fine, the cost reached from me to y is 1, so 1 plus 60 is 61. So it enters 61 here, but it rightly selects the least cost, which is the direct cost from z to x, and it informs y that look, the cost reached from me to y is what, 50, and y from me to x is 50, and y says, okay, fine, my cost from my cost to reach to z is 1, so 50 plus 1 is 51, right? So after, you can see, after 3 iterations, the algorithm will terminate, will converge if we Poisson the reverse path, and otherwise, because of the loop here, we had this count to infinity problem where we have to do a lot of iterations in order to have the algorithm in a stable state. Before moving towards the scalable routing and discussing Water Gateway Protocol, let's talk about RIP that makes use of this distance vector routing algorithm. So let's quickly talk about routing information protocol. RIP. You should have implemented RIP in your lab. So RIP is basically it's an implementation of distance vector algorithm. It's an implementation. Of distance vector algorithm. And it was first was part of Berkeley's software distribution Unix in 1982. And here the distance metric is basically the number of hops. Distance metric is number of hops, and we have just discussed that maximum we have 15 hops allowed. And if I use number 16, this means this represents infinity. So 16 hops represents infinity, and we use this number to count to infinity problem by poisoning the reverse path, right? So what happens in RIP is that RIP sends this distance vector after every 30 seconds, right? So distance vector, or this cost, is sent, or you can say advertised, once every 30 seconds. And if and it takes 8 minutes to count to infinity, right? And it takes detect loop if we rely only on periodic updates. And the link failure info is quickly propagated with triggered updates. So it uses triggered updates to quickly propagate link failure. Link failure information. Okay, and then most importantly, we did discuss last time that OSPF is sent over IP without using any TCP or UDP here. These distance vector updates, or the distance vectors, are sent using UDP. So these distance vectors are sent using user datagram protocol, right? And if there are no advertisements heard from a neighbor in 180 seconds, this means the neighbor or the link is declared down, right? So we declare a link or neighbor down. So neighbor or link is declared down if no update or advertisement after 180 seconds. Okay, and all the routers via neighbors or the routes via neighbors are invalidated, and all the neighbors that this link is no more available. By the way, it's important to note here is that RIP routing table is managed by application level process. So RIP routing tables are managed by application level process called route daemon, route D or route daemon. Okay, right. Let's go back and to the slide set and talk about the scalable routing. Now, the problem here is that up till now, we have assumed a simple scenario, right, where we are assuming that all the routers are identical in a network or the networks are flat, but this is not true. Routing is more complex with more routers and more destinations, say millions of destinations, right? So 300 million plus destinations are there in the world. So we need to have a routing table that is scalable, right? If I do not use a scalable router, this means this will take more time to compute routes, right? And I have to use more link of the bandwidth for the routing updates. And the second point is that we want to have administrative autonomy here, right? Because internet is the network of networks. So each network administrator may wants to control routing in its own network. So this means the algorithms that we have discussed so far, or the routing protocols like OSPF and RIP that we have discussed so far, are not scalable. Why? Just take the example of, for example, just take the example of link state. So what happens in link state routing algorithm, or what happens in OSPF, which is based on link state? Every node has the information, complete topology information. So this means my router has to have a huge space where I can store 300 million plus entries in one table. And think about the searching time required in that table having 300 millions plus destinations, entries, right? Does it seem feasible to you? No, it does not. And what do you think? What about the DV that we just have discussed, or the routing algorithm, the routing protocol that is based on it, routing information protocol? There are a lot of update messages, right? So every router has to inform its neighbors, and the neighbors will inform the update to their neighbor, and then so on and so forth, right? So what we'll do, we will use a lot of bandwidth link in sending the route updates only, right? So this means we have to come up with a solution that is that supports scalable routing, where the size, when the size is increasing, we can handle it efficiently without considering the space problem or the bandwidth problem by sending route update messages. So the solution is hierarchical routing. So what we have done is we have divided this internet world into autonomous systems. Every network is an autonomous system, right? So we aggregate the routing information into autonomous system, AS. So we have two types of routing algorithms now, or protocols. There are protocols that are used for intra-autonomous system routing that will be using within an autonomous system, right? Or there will be protocols, routing algorithms that will be using for inter-autonomous systems routing, okay? And every autonomous system has a boundary router or a gateway router. So it's a special router. Its job is to, propagate or aggregate the information inside the autonomous system and communicate the reachability to other autonomous system, to all the routers inside an autonomous system. So let's try to understand it with the help of this example. So here we can see three autonomous systems here. There are three autonomous systems: C, A, and B, right? So in autonomous system C, I can use intra-autonomous system routing. So there are two types of routing here. So we have intra-autonomous system and inter-autonomous systems. If I want to route data from A to B inside this C autonomous system, this is called intra-autonomous system routing. And if I want to route data from C to A using these two boundary routers or gateway routers, that is CB means B router of autonomous system C and A router of autonomous system A. Now this link is, by the way, inter-autonomous system routing. So what we have done is we have break down a problem into a hierarchy. So at the first level, we have routing between the autonomous systems, and then we have routing in between the different autonomous systems, right? So for example, I can make use of RIP here in autonomous system C, or I can make use of OSPF here in autonomous system A. We know this, that it has it has scalability problem. So I'm not expecting to have a very huge number of router within an autonomous system, right? And similarly, maybe I can use Cisco's interior gateway routing protocol, IGRP, within this, which is proprietary, which is implemented in autonomous system B for intra-autonomous system routing. Okay, so for when I talk about this inter-autonomous system routing, means the communication between the gateway router of autonomous system C and gateway router of autonomous system A, means this link or this link or this link, right? Okay, or this link. So this is a problem of inter-autonomous system routing, and there is only one de facto standard of routing protocol here, known as Border Gateway Routing Protocol, and its version 4 is being used at the moment. So BGP is the de facto standard for routing in between the autonomous system. For inter-autonomous systems routing, we use Border Gateway Protocol version 4. Right. So we can see if host 1, host H1 in autonomous system A wants to communicate with host 2, host 2 in autonomous system B, what happens? First, we'll have this routing within this autonomous system, right? And then we will have this routing between different autonomous systems, which is inter-autonomous system routing. And then again at the autonomous system B, we have this routing to do within the autonomous system B, means intra-autonomous system routing. Okay, and as I discussed earlier, we can have different protocols for intra-autonomous system routing, but for inter-autonomous system routing, means for this link, there is a de facto standard that is called Border Gateway Protocol version 4. Okay, so for internet routing, we have a variety of algorithms. Some of these we have covered. So one is based on link state. We have covered it, and yes, we know that it's used for intra-autonomous system routing, and similarly, we have covered this routing information protocol, and it is also used for intra-autonomous system routing. And whereas this BGP is for Border Gateway Protocol version 4 is for inter-autonomous system routing. Okay, so this diagram shall help us to understand the working of Border Gateway Protocol, which is the de facto standard for routing in between the different autonomous systems. Okay, so what BGP, Border Gateway Protocol, provides each autonomous system is a mean to obtain reachability information from the neighboring autonomous systems. So using BGP, what this autonomous system AS2 can do is it can get the reachability information about the autonomous system 1, means all the network prefixes. Remember, in BGP, individual host is not the destination. BGP, the destination is the network prefix, right, or subnets that we want to reach to. And then we can propagate the reachability information to all the routers internal to an autonomous system. So for example, using this reachability information, autonomous system 2 can inform all of these routers the reachability information about an autonomous system 1, right? And it's the job of the the BGP to determine the good route to subnets based on the reachability information, and also that we'll discuss in a minute on the autonomous system policy, which is very important to cover. Right, so what happens in these autonomous systems using BGP is that the BGP allows each subnet to advertise the existence to the rest of the internet. For example, a subnet here in the autonomous system will tell autonomous system 2 about its existence, and then it will be shared with autonomous system 3, and so on and so forth. Okay, so in this example, the routers that communicate using this BGP protocol are called BGP peers. So, for example, at the moment, these two routers are communicating using BGP, and these two routers are called BGP peers, Border Gateway Protocol peers. Okay, and these peers basically these peers basically communicate using BGP connection that is called this. So this link or connection is called BGP session. So BGP peers communicate with each other using what? Using BGP session. And remember, this BGP session where these pairs of routers, where this pair of router exchange routing information is established over semi-permanent TCP connection. So this BGP session, using which these two BGP peers communicate with each other, is established over. So it's established over semi-permanent TCP connection on port number 179. So using port number 179, we'll establish this TCP semi-permanent TCP connection where this BGP peer or peers will exchange information, right? So, by the way, there are two types of session. The session between the gateway routers is called, there are two types of sessions here. So one session is called, between the one session between these gateway routers is called eBGP. So this session is called, in fact, eBGP, which is external BGP, where E stands for. So this session is the one that I have highlighted here is external BGP. Also, the session between these two routers, for example, router R5 and R1 in this autonomous system, is known as IBGP or internal BGP sessions. We call it internal BGP session. Okay, or we call it IBGP. Okay, so there are two types of sessions that are used to exchange the information, and most importantly, the information that an autonomous system can exchange with each other, with autonomous system 3 or autonomous system 1, is basically prefixes, right? So the information that an autonomous system can exchange is not individual host or destinations, but it's because it's classless inter-domain routing serialized prefixes. Right, since it's based on classless inter-domain routing, so we use subnetting based on classless inter-domain routing. So autonomous system will share all the subnet prefixes that are there, or what it can does is that it can advertise a single prefix to its neighboring autonomous systems, right? So remember, within an autonomous system, we can have either OSPF, or we can have RIP, or some other implementation like IGRP. But for the exchange of information between the autonomous systems, what we do, we need to have border gateway protocol, and for that we have two types of session. This IBGP session is used to communicate the subnet the prefix network prefixes that are advertised by R2 to R1 of autonomous system 1. So R1 will use this IBGP or internal border gateway protocol session to disseminate this reachability with other routers such as R5. So using the eBGP session between the gateway routers, for example, R2 and R1, R2 of autonomous system 2 and R1 of autonomous system 1. So autonomous system 2 sends what? The list of prefixes that are reachable from autonomous system 2. Okay, and similarly it sends same information to autonomous system 3, and if there would have been other autonomous systems, so this information might have been forwarded to the other autonomous systems, right? And similarly, when a gateway router in any of these autonomous system receives eBGP learned prefixes, the gateway router uses its IBGP session to distribute the prefixes to the other routers inside the autonomous system, as I've discussed earlier, right? So R will use IBGP session to share this information with R5 of autonomous system 1. Okay, so remember that when the path is shared between the autonomous system, or the reachability is shared, every autonomous system also share a globally unique autonomous system number. So every autonomous system has autonomous system number. We call it ASN. Right. So this globally unique autonomous system, and the details are, by the way, given in. If you want to look at its detail, it's there in RFC request for comments 1930. So when reachability is advertised, also the globally unique autonomous system number is shared with the neighboring autonomous system, right? So if we look at the autonomous system path vector, so it basically is because it's based on distance vector. So each border gateway broadcasts to the neighbor spheres, as we have discussed in the previous slide. So BGP routes to the network, not individual hosts. So as I've discussed, these are network prefixes, in fact. So rather than targeting individual host destination, the other important thing here that we want to discuss about BGP is the controlling the route, means controlling who routes to you. So look at this example. So in this example, we have two types of networks. So we have a provider network, right? For example, A, B, and C are ISPs, and then W, X, and Y here are customer network, right? So A, B, C are provider networks, means say these are ISPs here. Okay, and these are the customer networks. And importantly, you can see here that X is dual homed, means X is attached to provider B as well as provider C, right? And X maybe does not want to route from B via X to C. So X don't want to allow this path, right? So X will not advertise B this path. X will not tell B about path between X and C, because maybe X will has no monetary benefit out of it. So in this way, X can control paths from it. So if X advertise this path to B, so this means X will also be routing data to the other provider C in this case, right? So let's look at the other example here. So again, let's assume that A advertises to B the path AW means the data can be routed from A to W, and B advertises to X the path BAW, right? So X can route from B to A and then W. Should B advertise to C the path BAW? What do you think? Should B advertise this path to C? No. Why? Because B gets no revenue for routing. CBAW means that C will first send to B, and then from B to A, and from A to W, right? Since neither W nor C are B's customer, right? So why? Because it's just a collaborating ISP, and W is also not the customer. So B has no, benefit of sharing this path with C, right? So B wants to force C to route W via this path, right? So it does not share this path with C, okay? So B only wants to route to and from its customer from X, or from any other customer, say T, right? So in this way, it's more about the policy. So BGP is in fact more about controlling the traffic and the policy, that what we want to route and why we want to route. If there is no monetary, for example, gain here, which is no revenue involved here, so this means B will not advertise this path BAW to C. And in this way, C will be forced to send data to W via A, right, using path CAW. BGP has following different kinds of messages, and these messages are exchanged, as we have already discussed, that semi-permanent TCP connection is established to exchange messages on port number 179. So what are the different types of messages that are exchanged? We have the open message that opens the TCP connection to the peers and authenticates the sender. Then we have update message, where we send the updates or withdraw the old, where we send the updates about the new path, or we withdraw an old path. Then we send keep alive message that keeps the connection alive in the absence of. Yeah, for example, we have no update to transmit, but still we want to keep alive this session, BGP session. For that, we need to have keep alive message, and then we have this notification message to report errors in previous message, or to close down, tear down a connection. So what do you think? What's the difference between the intra-autonomous system routing and inter-autonomous system routing, right? So clearly there are three things to think about. Number one, policy. The inter-autonomous system is more about the policy, right? Means here admin wants to control how the traffic is routed and who routes through its net, as we have seen in the previous examples. But in intra-autonomous system, this is not the case. We are not really concerned about the policy. One admin, no policy decisions are needed. Nobody else is routing data through our network. And the second, the difference between the intra and inter-autonomous system routing is the hierarchical routing. We have divided the network world into different autonomous systems, reducing the table size, and also the updates that are required, right? And we have discussed this point earlier. What if we are using RIP and OSPF instead of Border Gateway Protocol? We'll be having huge table sizes, and there will be many number of updates. So we might have consumed all the available bandwidth by sending update messages, right? So it was not scalable, right? So intra-autonomous system routing algorithm protocols are not scalable, whereas inter-autonomous system routing protocols are scalable. And then talk about the performance. Inter-autonomous system here is not, about the performance. Here, policy dominates the performance. I'm not concerned about the performance here. Maybe I'm more concerned about the policy, right? That who routes data through my network. And whereas the intra-autonomous systems, RIP or SPF, other similar protocols, really focus on the performance rather than the policy, right? So this summarizes our lecture number 8, part B, where we discussed distance vector routing algorithm. We discussed that it belongs to dynamic programming, and it was basically enhanced by Ford Fulkerson, and that's why we call it Bellman-Ford algorithm. And RIP makes use of Bellman-Ford algorithm, and we also try to look at the working of Bellman-Ford algorithm and the problem of onto infinity problem in Bellman-Ford algorithm, and its possible solution by poisoning the reverse path. And then we discuss the details of RIP, routing information protocol, that makes use of distance vector routing algorithm. And then we discuss radical routing by discussing border gateway protocol. The border gateway protocol is very complex, by the way. We assume a very simple example to understand it. It's basic, operations. Dear students, thank you very much. Allah Hafiz.